In this video, we're going to cover the first part of section 3.5 in the linear differential equations class. I'd like to point out that the homework is going to be 1 through 7 and 11 through 15 for this section. And again, we're going to be covering the first half of this section 3.5, non-homogeneous equations, the method of undetermined coefficients. In this first half, we're just going to talk about what a non-homogeneous equation is, and then how to solve it, what the general solution will be, and then I will do one example, and then I will make a second video to follow up for 2 more examples. So let's get started. So first, what are we trying to do here? Well, we're going to now, we will see how to solve a non-homogeneous differential equation of the form L of y equal to y double prime plus p of t y prime plus q of t y equal to g of t. A reminder that we've solved the homogeneous differential equations of this of the form this equal to 0, but now we're going to add or put a function here in place of 0 at the end, and that is what we call a non-homogeneous differential equation. So we want to see how to solve that. Well, to do that, we have this theorem. And that is that the general solution of the non-homogeneous equation, given here again, is written in this form: y is equal to phi of t, which is c1 y of t, y1 of t, plus c2 y2 of t, plus capital Y of t, where y1 and y2 form a fundamental set of solutions of the corresponding homogeneous equation, and we've written out the homogeneous equation here. Again, that's the same equation as above, except equal to 0 at the end. And we know how to find y1 and y2 from the previous sections. And c1 and c2 are, of course, our arbitrary constants. But what is this capital Y of t? Well, capital Y of t is any solution to the non-homogeneous equation. So what we're going to have to do is we're going to have to find a single solution to the non-homogeneous equation, and the total general solution then will be the fundamental set of solutions here, so that general solution to the non-homogeneous equation, or sorry, to the homogeneous equation, plus one particular solution to the non-homogeneous equation. So again, since I've written here, since we already know how to find the general solution to the homogeneous equation, at least to the homogeneous equation with constant coefficients, we're going to turn our attention to finding the particular solution. And that is this, again, the solution capital Y of the non-homogeneous differential equation. So that capital Y we call the particular solution. Okay. So we are going to look at the method of undetermined coefficients now. And this is going to be our method for finding a particular solution. Okay, so we're going to use this method to find a particular solution, and we're going to start with an example. In fact, we're just going to do a bunch of examples from here on to the end of the section. But again, we'll start with this example, and that is find the particular solution of, or a particular solution of, y double prime minus 3y prime minus 4y equal to 3e to the 2t. Okay, so I want to try to find that. Now, the question might be, well, how do we do that, right? So the method of undetermined coefficients is all about guessing what the solution might look like. So the method of undetermined coefficients requires us to guess what the solution will look like. Okay. And here, if we look at our equation, we got an e to the 2t over there. And we notice that if we derive e to the 2t, we're just going to get e to the 2t as part of the term every time, no matter how many times we differentiate. So we might guess that y equal to c times e to the 2t for some constant c might be our solution, might be a particular solution. We don't know yet, but we'll actually find out that this is true very soon. But how do we do that? Well, first we want to calculate y prime and y double prime. So y prime is 2c e to the 2t, and y double prime is 4c e to the 2t. And now let's go back and plug into the original equation. All right, so our original equation was y double prime minus 3y prime minus 4y is equal to 3e to the 2t. So we plug that in, so we get y double prime, which is 4c e to the 2t, minus 3 times y prime, which is 2c e to the 2t, minus 4 times y, which was c e to the 2t. All right, so if we factor out e to the 2t here, we get e to the 2t times 4c minus 6c minus 4c. And all of that is equal to negative 6c e to the 2t. And what does that equal? Well, that equals 3e to the 2t, right? Because our original equation said that y double prime minus 3y prime minus 4y is equal to 3e to the 2t. So that's what we have here. So this gives us, again, negative 6c e to the 2t is equal to 3e to the 2t. This implies that when we divide by everything here, that c is equal to negative 1/2. And so we get y equal to negative 1/2 e to the 2t as our particular solution. And I leave that up to you to plug that back into the original equation and find out that it really is, in fact, 3e to the 2t once we plug it back into here. Again, this will be the end of the first half of section 3.5. I'm going to end this video now and then make a second video for 2 more examples, just so that it's easy to upload and the video size is smaller. All right, so that's the end of this one.